Ever heard of a single scientific paper completely changing the game for an entire industry? Well, today, we're diving into one from 2009 that did exactly that. At first glance, it might not look like much, but this paper by Tsutomu Miyasaka and his team quietly unleashed a new material that would totally shake up the world of solar energy. So let me just ask you this. What on earth does a crystal structure, first found way back in the 1830s in the Ural Mountains, have to do with the future of clean energy? I know, it sounds like a riddle, right? But the answer is, well, pretty much everything. And it's a fascinating story. All right, to really get this, we need to rewind a bit. The year is 2009, and the solar power world, it had a problem. Researchers everywhere were on the hunt for something new, something better to make solar cells more efficient and a whole lot cheaper. See, the big thing at the time was something called a dye-sensitized solar cell. But as the paper points out, they just weren't cutting it. The organic dyes they used to capture sunlight, they weren't great. They didn't absorb a lot of light, and they could only grab a really narrow slice of the spectrum. People were also trying out other fancy alternatives, called quantum dots, but they weren't doing much better, with efficiencies pretty much stuck in the 2 to 3% range. The field was desperate for a game changer. And this is where Miyasaka's team comes in and does something totally different. They decided to take a chance on a class of materials called Organometal Halide Perovskites. Honestly, it was a bit of a long shot, but these things had some really unique properties that made them an intriguing candidate. So what even is a perovskite? Well, it's not one specific thing. It's any material that shares this very particular crystal structure with the formula ABX3. The ones they used here are cool hybrid, mixing simple organic parts and inorganic parts. We're talking common, abundant stuff like lead, carbon, and iodine. Now, the really cool part is the structure itself. You can see it here, straight from the paper. It forms this incredible, cage-like lattice. You could almost think of it as the perfect tiny architecture for trapping photons of light and shaking electrons loose. This unique structure, that's the secret sauce. Okay, so they've got this awesome material. The next big question was, could they actually build a working solar cell with it? Turns out the process they came up with was surprisingly simple. They essentially built a tiny, high-tech sandwich. They started with a piece of conductive glass and then printed on a layer of titanium dioxide. Yep, the same white stuff you find in sunscreen. This layer was mesoporous, which just means it's like a microscopic sponge, giving it tons of surface area. Then came the magic. They dropped a liquid solution of the perovskite ingredients onto the surface and spun it incredibly fast. This move, called spin coating, forced all those chemicals to snap together and self-organize into that perfect crystal layer. From there, they just added an electrode and an electrolyte, and boom, the cell was complete. Okay, the cell is built. Now for the main event. The researchers didn't just test one kind of perovskite. Oh no, they staged a head-to-head showdown between two slightly different versions to see which one would come out on top. In this corner, we have Team Bromide, and in the other corner, Team Iodide. The only real difference between them is one little element, bromine versus iodine. But that tiny change had a huge, visible effect. The paper notes the bromide mixture turned yellow, while the iodide turned black, which is a pretty good clue that it was absorbing a whole lot more light. In this slide, wow, it just lays out the whole story. Let's look at these two graphs. Graph A on the left shows us how much light each one absorbs. See that solid line? That's Team Bromide. It kind of gives up early. But the dashed line, Team Iodide, just keeps on soaking up light way out into the red and infrared, up to 800 nanometers. Now look at graph B. This shows the trade-off. Bromide, the solid line, produces a really high voltage, which is great. But iodide, the dashed line, generates way, way more current. So who wins? Well, let's look at the tail of the tape. This table breaks it all down. You can see Team Bromide won big on voltage with a very impressive 0.96 volts. But look at the current. Team Iodide is a powerhouse, delivering double the current at 11 milliamps per square centimeter. And in the solar cell game, current is king. So, what was the final score? The iodide-based cell achieved a final power conversion efficiency of 3.81%. Now, I know what you're thinking. 3.8%? That sounds tiny. And you're right, it does. But you have to understand, in 2009, for a first try with a totally new material, this number was absolutely revolutionary. And that brings us to the real breakthrough.
Why on earth did this seemingly small number send such a massive shockwave through the entire scientific community?
The authors themselves said it best, right in their conclusion. This efficiency is significantly higher than those obtained to date with non-organic sensitizers and quantum dots. In just one sentence, they announced to the world that their new material had just leapfrogged the other technologies that researchers had been working on for years, just trying to crack that 3% barrier. So you see, the real legacy of this paper wasn't the 3.81% itself. It was the proof of concept. It was a signal to researchers everywhere that this perovskite crystal structure had unbelievable potential. It was like striking oil. This one paper kicked off a global research gold rush, and in just one decade, scientists pushed perovskite solar cell efficiencies past 25%, right up there with traditional silicon.
And that's the story of the paper that started it all. It was the critical first step, but it leaves us with the huge questions researchers are still wrestling with today. How do we solve the durability problem and make these things last for decades? And what will it take to finally scale this incredible technology up for the whole world? The race that this paper started back in 2009 is far from over.